Hello and welcome. This is the third and final lecture on chapter 44. Today we'll be talking about radioactivity. In this drawing, we see a photographic plate that has been darkened after being exposed to radioactivity. Henry Becquerel, one of the founding parents of the field of radioactivity, discovered that after he left some sulfate crystals by a photographic plate, that the plate had been darkened, which meant that radiation had been produced by these crystals and struck the plate. Considering that he had a sort of screen on the plate to protect it from light, whatever the crystal was radiating was strong enough to penetrate into the plate. So he concluded that there's just some radiation produced by the crystal that occurs on its own and is strong enough to affect this photographic plate. And so there's some energetic radiation coming off this crystal, and it's just occurring randomly and spontaneously. And so the field of radioactivity was born. Another pioneers in the field were the husband and wife super duo, Marie and Pierre Curie, or Curie, who, in their studies of radioactive elements, unearthed actually some natural occurring radioactive ores, and in doing so, discovered two previously unknown elements, polonium and radium, which are both unstable and were therefore radioactive. And they studied them thoroughly. In fact, Marie Curie won two Nobel Prizes, one with Pierre and Becquerel for their study of radioactivity, and another for discovering polonium and radium. So, from further studies of these unstable elements that were producing this, strong radiation just spontaneously and randomly, they realized that as these radiations kept occurring, the amount that they had of these radioactive elements was decreasing. So it seemed that the nuclei of these elements of the sample that they had was decaying as radioactive activity went on. Turns out that there's three types of radiation that can occur. And the reason that happens is because radioactive substances are just things, you've heard of uranium or even some isotopes of, say, radon and potassium. They're basically elements that have unstable nuclei. So these nuclei being unstable, they want to reconfigure themselves into a new nucleus that is actually stable. And so in doing so, they end up decaying in one of three forms to reach a more desirable state. The first type of decay is the alpha decay. Alpha decay is when what used to be called an alpha particle, which is in fact a helium nuclei, is emitted, and this also transforms the original radioactive nucleus into a different, more stable nucleus, and also produces the alpha particle. Beta decay can also occur in radioactive elements where either an electron or a positron is emitted. We called either one a beta particle. If you're wondering what a positron is, it's actually the antiparticle of an electron. It has the same weight and opposite charge. Finally, there's the gamma decay, where an excited nucleus releases electromagnetic energy in the form of a high energy photon in order to stabilize itself. And the way that you can tell these apart, because unstable nuclei can produce all kinds of decay, the way that you can tell an alpha or beta or gamma ray apart from each other is by having the radioactive sample next to a magnetic field, because and that will deflect the alpha particles one way, the beta particles the other way, and the gamma ray will not be affected, so it'll go straight through. And even if a beta particle has the same charge as the alpha particle, if it's a positron, its deflection will be slightly different due to the difference in mass between the alpha particle and the positron. Also, I just now been calling them alpha rays and beta rays, but the proper term is alpha particle and beta particle. Also, despite the fact that alpha and beta and gamma decay are all part of radioactive decay of a particle of a sorry of an radioactive element, the word radioactivity implies radiation, like electromagnetic radiation, but that's sort of a kind of like a grandfather term by now, because right, alpha and beta radiation is no radiation at all. It's actually particles being emitted through radioactive decay. So the only thing that's an actual ray is the gamma decay that actually produces electromagnetic radiation. So a single decay, whether alpha, beta, or gamma, the particle that gets produced out doesn't do much by itself. An alpha particle just barely penetrates paper. A beta particle can go a few millimeters into aluminum. A gamma ray, though, it is fairly powerful. It can penetrate a few centimeters of lead. So a single radioactive nuclei, will only produce one of these outputs. So, a few atoms of uranium won't do much harm. One alpha particle or beta particle will be produced, per couple of years. But when you have a large sample of radioactive matter, then the decays do happen at a faster rate, and thus they're the source of constant alpha, beta, and gamma particles, which can harm the environment and living beings in the surroundings. Interestingly, we do have some radioactive elements in our own bodies. We have a isotope of potassium, potassium 40, that is actually unstable. Its rate of radiation is pretty slow, and we don't have that much of it. So whenever it decays, its effect is less than a tickle to our internal system. Funnily enough, potassium 40 is contained in a banana. So whenever you eat a banana, you're ingesting radioactive material. Don't worry, it's very, very little. And the body's metabolism tries to keep a constant amount of potassium. So um, if you eat a banana every day of the week, it won't accumulate. Your body will discard the potassium it doesn't need. So you're safe from bananas. They're harmless. So just because something is radioactive doesn't mean it's constantly, emitting these particles and affecting everything in surroundings. It's only when there's large amounts that the radiation can become uh, dangerous. Also, I should point out that gamma rays can, cause harm to the body if they're intense enough. You will not become the Hulk. If anything, a really strong gamma ray by itself hitting your body can actually have the same impact that a baseball flying towards you at 90 miles per hour would. It will actually hurt to get hit by a really energetic photon. Now, we've seen that the Curies and Becquerel saw that radioactive sources just decay spontaneously, randomly, but there's still an average decay rate that can be observed. So, on average, some elements decay more faster than others. This leads to a decay constant, which is the average decay rate, or more specifically, it's the average probability of the nucleus of a particular sample to decay in some unit time. So on average, how long does it take for one nucleus to decay? That's what lambda measures. So for large lambda, for a large decay constant, it means that you expect decays to occur more often than not. So when you have a sample, the amount of sample that you have over time drops off pretty fast. While for a small lambda, on average, decays take a bit longer. So the decay, the disintegration of the sample occurs over a longer period of time. Now, then the amount of sample that you have left over time as it decays, whether that's alpha, beta, or gamma decay, doesn't matter. It just keeps disintegrating itself. You keep losing some of that original element. Um, that actually follows an exponential curve. So over time, the amount of sample that you have drops off exponentially. You can figure out how much sample you have after some time t using this formula here. You just need to know the decay constant that accounts again for the average rate of decay, and also you need to specify how much of the sample you started off with, NO. You can also calculate the decay rate, which is proportional to the amount of sample that you have, because the more you have of a radioactive element with you, the more decays you'll observe per unit time, since despite decays being spontaneous and random, the more you have something, the more likely it is that it'll occur. So the decay rate, similar formula to the n, the number of nuclei left after some time. It basically is proportional to the initial decay rate when you start off with your sample at full, and it'll tell you how much it is after your sample has been decaying for some period of time. The unit then of the decay rate is just literally, one nuclei decaying per second, or one decay per second. If you want to be formal and use SI units, that's equal to 1 becquerel or 1 BQ. And radioactive physicists, people who study radioactivity, not people who are radioactive, tend to use the Curie unit, which is equal to 3.7 times 10 to the 10 decays per second, which is actually a pretty fast rate of decay. So the most common use of the unit is in millicuries or microcuries. The reason why it's defined this way because it's the decay rate of 1 gram of radium, which, by the way, sometimes we use the word activity to refer to the decay rate. You may have noticed that the markings on this graph that shows you how over time the sample that you have keeps decaying, but notice how the rate kind of slows down the less and less you have. Note that after some time you're left with half the amount you had, and then after some time you had half of that half. You have a quarter of the initial sample. There's this half-life, which is how long it takes for a radioactive substance to annihilate to the point where there's only half of what you originally had. And this is actually a function of the decay rate. So if you know the decay rate, you can calculate it with the formula here. And the faster the decay rate, and the shorter the half-life. So after one half-life, you've lost half of your initial sample. And then after two half-lives, you'll have lost 3/4. So half-life is measured with respect to what you currently have. So you have 10 grams of cobalt-60 after one half-life. So after, in the case of cobalt-60, if 5 years have passed, you'll have 5 grams left. When another 5 years passes, you'll lose half of what you had. So you'll have 2.5, then you'll lose half of that after 5 years, you'll have 1.25, and so on. And if you know how much time passed in terms of half-lives, so, if 10 years have passed, that's about 2 half-lives of cobalt-60, then you can easily calculate the amount of sample you have left by taking the original amount times 1/2 to the power of the number of half-lives that have passed. So here's a table here showing you the half-lives of different radioactive elements. Note that some are very fast and active, And you might think that, that does make them dangerous because they're radiating particles really quickly. And while true, it also means that any sample of them would decay fairly quickly into, that would just become some stable element instead. So it wouldn't be much of a problem if you just wait them out. And if you look at stuff like uranium, which, in popular media is considered a very radioactive element, you look at the half-life and you think, oh, well, 700 million years. So uranium's not that active then. It's pretty harmless, which might seem like a good thing that its decay rate is probably so slow, but it's actually a bad thing because that means that uranium on its own will take forever to decay while still radiating away. So uranium will affect its surroundings over incredibly long periods of times, slowly contaminating everything with radiation, which is why uranium, it's hard to get rid of it because it won't decay fast enough. It will not turn into something stable fast enough like lithium or krypton would. Then the best thing to do is store it far away from everything else, cover it in lead, and put it in a basement somewhere. To give you an idea of the problem of, long of slow decay rates, the suits worn by the firefighters who went to put out the fires in Chernobyl are still locked away because they're still emitting radiation. They're still toxic to be around. Anyways, to end it on a brighter note, the quick quiz here talks about having a sample of bismuth, doesn't really roll off the tongue, a sample of bismuth given to you on your birthday. And every 5 days or so, half of the current sample decays. That's a half life. So when it's given to you, its activity is about 1 millicurie. But after 1 year has passed, your next birthday, what's activity going to be? So your sample has decayed quite a lot by your next birthday. So then the activity will also decrease. You can figure out then how many half-lives have occurred in that time. Given that 1 year is 365 days, about 72.9 half-lives have passed. So you can find the activity after that many half-lives by just taking the formula normally used for number of sample left after n half-lives and just use that for the activity instead. Note that for this formula, n doesn't have to be a discrete number. So like, you're between 72 and 73 half-lives right now, but that's okay. And it's actually okay to measure, decimal number of half-lives. It still works into the formula here. So after 72.9 half-lives have passed, the decay rate, the activity, you plug in everything to the formula, you plug in the initial decay rate, and the thing has such a slow decay rate compared to what you initially have, since a lot of time has passed. And thus the answer is D, and I included the textbook answer as well. And there's a few examples from the textbook here. Again, I recommend you look at them. They're good for practice. You should be comfortable using the decay formula to, get the decay rate after some time has passed, or even to calculate how much time has passed if you know the initial and final decay rates. So to get that, if you know the initial activity and the final activity, such in this question where you're given an initial activity of 5 millicuries and you're told that after some time you have 2.1 millicuries of activity, then you should be able to figure out how much time has passed. Now, you can also kind of guesstimate, because you're told that the half-life is 8 days, and here the activity has dropped by a bit more than half. So you can then expect that about a time equal to around the half-life must have passed, which is true. If you calculate it, 10 days have passed. So you should be comfortable with the algebra here. You're trying to calculate the time to go from one activity to another. So to get rid of the exponential e here, you have to take the natural log of both sides. In doing so, you can isolate for t and get the answer in units of days. So to get rid of e, you take ln of both sides. And that brings the exponential terms here to the main part of the equation. And you just have to deal with taking the natural log of r over r naught, and then you're done. Anyways, that's all for now. And we'll want to see you next time, as this is the final recorded lecture covering the textbook as part of this course. But I hope to see you for the final review. Thank you.